All right, we'll continue our discussion on chapter 17, test and evaluation. We were just starting to get into some of the details. And so let's get into just a second. Okay, we'll continue our discussion on the major concepts of this chapter, but let's begin by thinking about aspects of test planning and preparation. So the typical activities include reviewing system requirements and defining detailed plans for integration and system test, defining the test requirements and functional architecture. Development system tests. The activities typically include performing system level test over the entire operational regime and comparing system performance with expectations, developing test scenarios, exercising all system operating modes, eliminating all performance deficiencies. In terms of operational test and evaluation, the typical activities include performing tests of system performance in a fully realistic operational environment under the cognizance of an independent test agent, and measuring the degree of compliance with all operational requirements and evaluating readiness of the system for full production and operational deployment. For agile system engineering testing, agile principles are also applied to testing the incremental products that are developed. Through engagement with the customer or end users, there is a better alignment of designing to coding than to testing. The alignment may occur through more frequent and richer communication between the developers, testers, and users. So we'll have a couple references that in the textbook for individuals. So Weiwei in 2016, his research on agile projects that adopt the Scrum approach with a 3-month delivery cycle and 2-week life cycle enabled the cross-functional team to decompose a finer level of detail in the product to enable this alignment. Agile methods were studied in the selected DoD defense programs as the development team focused and refined the requirements as the software developers were conducting their development, which was found to be superior than the method of simply implementing requirements that were decided long before the developers had the role in understanding the user needs. Agile teams would hear the customer story, specify the requirements, write test cases based on these requirements, refactoring to add and test new features and demonstrate the capabilities. Werbel and other et al. From 2014 evaluated the testing method in agile software development projects. Their observations led to automating the test procedures as much as possible and could allow more insight into the quality of the software products being developed. A regression test approach was taken with each sprint to evaluate the existing and newer features through a continual integration and testing approach. This was found to build confidence in the project and help to avoid surprises at the main testing milestones. The sprint approach assisted with the development of building only what is necessary for the system. In terms of the physical test and configuration, integration testing requires versatile and readily reconfigurable integration facilities. To understand their operations, it is useful to start with a generic model, the system element test configuration, and that's what we're showing here now. And so we'll talk about these elements next. So for the system element, under test is represented by the block at the top of the center figure. The input generator converts the test commands into exact replicas functionally and physically of the input that the system element is expected to receive. These may be a sequence of typical input covering the range of expected under operational conditions. The input signal in the same or simulated form are also fed to the element model. The output analyzer converts any outputs that are not already in terms of quantitative physical measures into such form, whether or not the data obtained in the test are compared in real time with predicted responses from the element model. They should also be recorded along with the test input and other conditions for subsequent analysis. In the event of discrepancies, this permits more detailed diagnosis of the source of the problem and subsequent comparison with results of suitably modified elements. The element model, which is pictured in the center of the figure, has the function of reproducing very precisely the response that the component or subsystem under test is expected to produce to each input according to its performance specification. The element model may take several forms, and in extremes, it may be a specially constructed and validated replica of the system element itself. At the other, it may be a mathematical model of the element, perhaps as simple as a table lookup if the predicted performance is the explicit function of the input. How it is configured determines the form of the input required to drive it. The test manager down here introduces a function not represented in the basic architecture of the figure. We're referring here to the Venn diagram that we showed a couple of slides before this. Because the testing of most elements of complex systems is a complicated process, it requires active supervision by a test engineer, usually supported by a control console. This allows critical test results to be interpreted in real time in terms of required performance so that the course of testing can be altered if significant deviations are observed. The performance comparator matches the measured system element output from the expected outputs from the element model in accordance with the test criteria provided by the test manager. The comparison and assessment is performed in real time whenever practical to enable rapid diagnosis of the source of deviation from expected result, as noted previously. Evaluation criteria are designed to reflect the dependence of the observational performance on individual performance parameters. So most actual test configurations are considerably more complex than the simplified figure that we're showing. So for example, tests may involve simultaneous inputs from several sources involving various types of signal elements, each requiring a different type of signal generator. Similarly, there are usually several outputs necessitating different measuring devices to convert them to the forms that they can be compared with predicted outputs. The test may also involve a series of programmed inputs representing typical operating sequences, all of which must be correctly processed. So it's clear from what we just discussed that the functionality embodied in the test configuration of a system test element is necessarily comparable with that of an element itself. Hence, designing the test equipment is itself a task of comparable difficulty with that of developing the system element. One factor that makes the task somewhat simpler is that the environment in which the test equipment operates is usually benign, whereas the system operating environment is often severe. On the other hand, the precision of the test equipment must be greater than that of the system element to ensure that it does not contribute significantly to measure deviations from the specified test performance. Next, for test conduct and analysis, the determination of whether or not a given step in the integration process is successful requires matching the output of the partially assembled components against their expected values as predicted by the model. The effort required to make the comparison depends on the degree of automation of the test configuration and of the analytical tools embodied in the performance comparator block that we're showing in the figure. The trade-off between the sophistication of the test and analysis tools and the analysis effort itself is one of the critical decisions to be made in planning the integration process. The scheduling and costing the integration effort, it must be expected that the numerous deviations will be observed in the measured performance from the predicted by the model, despite the fact that all the components presumably have previously passed qualification tests. Each discrepancy must be dealt with by first documenting it in detail, identifying the principal sources of the deviation, and devising the most appropriate means of eliminating or otherwise resolving the discrepancy. It should be emphasized that in practical practice, most failures observed during the integration process are usually due to causes other than the component's malfunctions. Some of the most frequently occurring problem areas are faulty test equipment or procedures, misinterpretation of specification, unrealistically tight tolerances, and personnel error. These are, we'll talk about these next year. So there are several reasons why faults are frequently found in test equipment. One, the amount of design effort allocated to design and fabrication of test equipment is far smaller than that of the effort spent on component design. The test equipment must be more precise than the components to ensure that its tolerances do not contribute significantly to observing deviations from predictions. 3, the equipment used to test separately an individual component may not be exactly the same as that incorporated into the integration test facility, or its calibration may be different. And 4, the prediction of expected performance of the element under test by the element model may be imperfect due to the impossibility of modeling exactly the behavior of the test equipment. Not infrequently, the specifications of the interface and interactions among the components permit different interpretations by the designers of the interfacing components. This can result in significant mismatches when the components are assembled. There's no practical and foolproof method of entirely eliminating this source of potential problem. The number can, however, be minimized through critical attention to and review of each interface specification prior to its release for design of the associated hardware or software. In most cases, establishing an interface coordination team, including all informed contractors, has proven to be advantageous. To ensure that interfacing mechanical, electrical, or other elements fit together and interact properly, the specifications for each separate element must include the permitted tolerances and the interacting quantities. For example, if the interface components are held together by bolts, the location of the bolts in each component must be specified within a plus-minus tolerance of their nominal dimensions. These tolerances must allow for the degree of precision of a production machinery, as well as the variation of the size of standard bolts. If the specified tolerances are too tight, there will be excessive rejects in manufacture. If too loose, there will be occasional misalignments causing fit failures. Personnel errors are a common source of test failures and one that can never be completely avoided. Such failures may occur because of inadequate training, unclear or insufficient detailed testing procedures, overly complex or demanding test methods, fatigue, or simple carelessness. Errors of this type can occur at any point in the planning, execution, and support of the testing process. For changes, if the diagnosis of a faulty test traces the problem to a component design feature, it is necessary to undertake a highly expedited effort to determine the most practical and effective means of resolving the problem. At this stage of development, the design should be under strict configuration management. Since any significant change will be costly and potentially disruptive, all means of avoiding or minimizing the change must be explored and several alternatives examined. The final decision will have to be made at the program management level if significant program costs and schedule changes are involved. If there is no quick fix available, consideration may be given to seeking a waiver to deviate from a certain specification from an initial quantity of production units so as to afford adequate time to design and validate the change prior to its release for production. Not infrequently, careful analysis reveals that the effects of the deviation on operational performance is not sufficient to warrant the cost of making the change, and a permanent waiver is granted. System engineering analysis is the key to determining the best course of action in such circumstances and to advocating its approval by management and the customer. Next, we'll talk about developmental system testing. The system integration process was seen to be focused on ensuring that components and subsystem interfaces and interactions fit together and function as they were designed. Once this is accomplished, the system may, for the first time, be tested as a unified whole to determine whether or not it meets its technical requirements for example, performance, compatibility, reliability, maintainability, availability, safety, and so on. The above process is referred to as a verification that the system satisfies the specification. Since the responsibility for demonstrating successful system verification is a necessary part of the development process, is conducted by the systems developer and will be referred to as the developmental system testing. And that's what we're referring to here in this section. For system testing objectives, while the primary emphasis of development system level testing is on satisfaction of system specifications, evidence must also be obtained concerning the system's capability to satisfy the operational need of the user. If any significant issues exist in this regard, they should be resolved before the system is declared ready for operational evaluation. For this reason, the testing process requires the use of a realistic test environment, extensive and accurate instrumentation, and a detailed analysis process that compares the test output with predicted values and identifies the nature and source of any discrepancies to aid in their prompt resolution. In a real sense, the test should include a rehearsal for operational evaluation. In the case of complex systems, there are frequently several governing entities in the acquisition and validation process that must be satisfied that the system is ready for full-scale production and operational use. These typically include the acquisition or distribution agency, which has contracted for the development and production of the system, and in the case of products to be used by the public, one or more regulatory agencies concerned with conformance with safety or environmental regulation. In addition, the customer may have an independent testing agent who must pass favorably on the system's operational worth. In the case of a commercial airliner, the customer is an airline company, and the certification agency is a Federal Aviation Administration, FAA, and the Civil Aeronautics Board, the CAB. For military systems, the customers are the service acquisition agencies, each of which has an operational test arm, such as the Navy Operational Test and Evaluation Force. An essential precondition to system integration testing has been successfully completed and documented. When system test failures occur in components or subsystems because of insufficient testing at lower levels, the system evaluation program risks serious delays. Required stand down at this point in the program is time-consuming, expensive, and may subject the program to critical management reviews. It is axiomatic, therefore, that the system test program should not be started unless the developer and customer have high confidence in the overall system design and the quality of the test equipment and test plans. Despite careful preparation, the test process should be conducted with the expectation that something may go wrong. Consequently, means must be provided to quickly identify the source of such unexpected problems and to determine what, within the bounds of acceptable cost and money and time, can be done to correct them. System engineering knowledge, judgment, and experience are critical factors in the handling of such late-stage problems. For development test planning, the provision of the defense temp regarding developmental testing and evaluations state in part the plan should define the system technical parameters to be measured, summarize test events, test scenarios, and the test design concept, list all models and simulation to be used, and describe how the system environment will be represented. For the system test configuration, testing requires that the test configuration be designed to subject the system under test to all of the operational inputs and environmental conditions that it is practical to reproduce or simulate, and to measure all the significant responses and operating functions that the system is required to perform. The sources for determining which measurements are significant should be found largely in system level requirements and specifications. The principal elements that must be present in the system test configuration are summarized next and discussed in the subsequent portions that we'll get to in a little while in the next section. So for system input and environment, one, the test configuration must represent all conditions that affect the system's operation, including not only the primary system input, but also the interaction of the system with its environment. Two, as many of the above conditions as practical should be exact replicas of those that the system will encounter in its intended use. The other should be simulated to realistically represent their functional interactions with the system. And three, when the real operational inputs cannot be reproduced or simulated as part of the total test configuration, special tests should be carried out in which these functions can be reproduced and their interactions with the system measured. For the system outputs and test points, we have 3 points here. So first, all system outputs required for assessing performance should be converted into measurable quantities and recorded during the test period. Two, measurements and recording should be made of all the test inputs and environmental conditions to enable correlation of the variation in inputs with changes in outputs. And three, a significant number of internal test points should be monitored to enable tracing the cause of the deviation from expected test results to their source in a specific subsystem or component. And last, for the test conditions, we have 3 points. First, to help ensure the contractor system testing team leads to successful operation evaluation by the customer, it is important to visualize and duplicate insofar as possible the conditions to which the system is most likely to be subjected during the operational evaluation. Two, some system tests may intentionally overstress selected parts of the system to ensure system robustness under extreme conditions. For example, it is common to specify that a system degrade gracefully when overstressed, rather than suddenly crash. This type of testing also includes validating the procedures that enable the system to recover to full capability. Finally, whenever practical, customer operating and evaluating agent personnel should be involved in contractor system testing. This provides an important mutual exchange of system and operational knowledge that can result in better planning, better planned and more realistic system test and more informed test analysis. Well, continuing on in this section, let's talk about some more areas in developmental system testing. First of all, let's talk about the development of test scenarios. In order to evaluate a system over the range of conditions which it is expected to encounter in practice, as defined in top-level system requirements, a structured series of tests must be planned to explore adequately all relevant cases. The test should seek to combine a number of related objectives in each test event so that the total test series is not excessively prolonged and costly. Further, the order in which tests are conducted should be planned so as to build upon the results of preceding tests, as well as to require the least amount of retesting in the event of an unexpected result. Composite system tests of the type described above that we just talked about are referred to as the test events conducted in accordance with test scenarios, which define a series of successive test conditions to be imposed on the system. The overall test objectives are allocated among a set of test scenarios, and these are arranged in a test event sequence. The planning of test scenarios is a task for systems engineers with the support of test engineers because it requires a deep understanding of the system functions and internal and external interactions. The combinations of several specific test objectives with a given scenario usually requires that the operational or environmental inputs to the system must be varied to exercise different system modes or stress system functions. Such variation must be properly sequenced to produce maximum useful data. Decisions have to be made as to whether or not the activation of a given test event will depend on successful results or successful results of the preceding unit. Similarly, the scenario test plan must consider what test results outside expected limits would be cause for interrupting the test sequence, and if so, when the sequence should be resumed. Well, let's talk about a couple of system performance models. I modified this chart just to spell out this acronym that I had here, but first let's talk about the system performance model before we get to the engineering development model. So for the system performance model in describing the testing and integration of the system components, a necessary element was stated to be a model of the components that predicted how it is expected to respond to a given set of input conditions. This model is usually either a combination of physical, mathematical, and hybrid elements, or wholly a computer simulations. In predicting the expected behavior of a complex system in its totality, it is usually impractical to construct a performance model capable of reproducing in detail the behavior of the whole system. Thus, in system-level tests, the observed system performance is usually analyzed at two levels. The first is in terms of the end-to-end performance characteristics that are set forth in the system requirements documents. The second is at the subsystem or component level where certain critical behavior is called for. The later is especially important when an end-to-end test does not yield the expected result, and is required to locate the source of discrepancy. Decisions as to the degree of modeling that is appropriate at the system level, at the system test level, are very much a system engineering function, where the risk of not modeling certain features have to be weighed against the effort required. Since it is impractical to test everything, the prioritization of test features and hence of model predictions must be based on system level analysis of the relative risk of omitting particular characteristics. The design, engineering, and validation of system performance and models is often a complex task and must be carried out by the application of the same system engineering methods used in the engineering of the system itself. At the same time, pains must be taken to limit the cost of the modeling and simulation effort to an affordable fraction of the overall system development. The balance between realism and cost of modeling is one of the more difficult tasks of system engineering. So we have the system performance model. Now let's think about the engineering development model. So as mentioned earlier, the system test process often requires that essentially all of the system be subjected to testing before the final system has been produced. For this reason, it is sometimes necessary to construct a prototype referred to as an engineering development model, EDM, for test purposes, especially in the case of a very large complex system. An EDM must be close as possible to the final production in form, fit, and function. For this reason, EDMs can be expensive to produce and maintain, and must be justified on the basis of their overall benefit to the development program. Okay, we have a few more things we want to be talking about. The system test concept, the conduct of contractor system testing is usually led by the test organization, which was also involved in the integration testing phase and is intimately familiar with the system design and operation. There are, however, numerous other important participants. For the test participants, we had a previous chart that looked at this. System engineers should have been active in the planning of the test program from its inception and should have approved the overall test plans and test configurations. Equally critical system engineering function is that of resolving discrepancies between actual and predicted test results. As mentioned previously, those may arise from a variety of sources and must be quickly traced to the specific system or test element responsible. A system level approach must be taken to devise the most effective and least disruptive remedy. Design engineers are also key participants, especially in the engineering of test equipment and analysis of any design problems encountered during testing. In the latter instance, they are essential to effect quickly and expertly such design changes as may be required to remedy the deficiencies. Engineering specialists such as reliability, maintainability, and safety engineers are essential participants in the efforts in their respective areas. Of particular importance is the participation of specialists in the testing of human-machine interfaces, which are likely to be of critical concern in the operational evaluation phase. Data analysts must participate in test planning to ensure that appropriate data are acquired to support performance and fault diagnostic analysis. So as noted earlier, while system testing is under the direction of the developer, the customer or the customer's evaluation agent will often participate as observers of the process and use the opportunity to prepare for the coming operational evaluation tests. It is always advantageous for customer test personnel to receive some operating training during this period. We also want to be talking about safety, where whenever system testing occurs, there must be a selection of the test plan for specifically addressing safety provisions. And so that's something that we also want to be considering, and there's more details in the textbooks. For test analysis and evaluation, test analysis begins with a detailed comparison of system performance as a function of test stimuli and environments. With that predicted by the system performance model, any deviation must trigger a sequence of actions designed to resolve the discrepancies. Then for diagnosing the source of discrepancies and all discrepancies in which the cause is not obvious, system engineering judgment is required to determine the most promising source of action for identifying the cause. This is always of the essence, but never as much as so in the middle of a system level evaluation. The cause of the discrepancy can be due to a fault in the 1, test equipment, 2, test procedures, 3, test execution, 4, test analysis, 5, the system under test, or 6, occasionally to an excessively stringent performance requirement. So all of those need to be taken into consideration and dealt with. In terms of dealing with system performance discrepancies, if a problem is traced to the system under test, then it becomes a matter of deciding if it is a minor and easily corrected or serious and or maybe not understood, in which cases there delays may be required or not serious and agreeable to contractors and customers that corrective actions may be postponed. So those are some of the details that are going on during the developmental system testing. There's more in the textbook you can refer to. Okay, next we'll talk about the operational test and evaluation. What does it actually mean that you have in terms of the results? So in previous periods of subsystem and system testing, the basis of comparison was a model that predicted the performance expected from an ideal implementation of the functional design. In system operational evaluation, the test results are compared with the operational requirements themselves rather than to their translation into performance requirements. Thus, the process is focused on validation of the system design in terms of the operational requirements rather than on verification that it performs according to the specification. The operational evaluation of a new system is conducted by the customer or by an independent test agent acting on the customer's behalf. It consists of a series of tests in which the system is caused to perform its intended function in an environment identical or closely similar to that in which it will operate in its intended use. The satisfactory performance of the system in meeting its operational requirements is a necessary prerequisite to initiation of production and deployment. In the case of systems built for public use, such as commercial aircraft, there are also be special tests or inspections by government agencies responsible for certifying the product safety, environment suitability, or other characteristics subject to government regulation. In terms of operational test objectives, the operational test and evaluation is focused on operating requirements, mission effectiveness, and user suitability. The subject of operation evaluation is usually a pre-production prototype of the system. The expectation is that all obvious faults will have been eliminated during development testing and that any further significant faults may cause some suspension of evaluation tests pending their elimination by the developer. The limitations of time and resources normally available for operational evaluation require careful prioritization of test objectives. A generally applicable list of high priority areas for testings include the following. And so first is the new featured. Features designed to eliminate deficiencies in a predecessor system are likely to be the area of greatest change and hence greatest uncertainty. Testing their performance should be a top priority. Environmental susceptibility. Susceptibilities to severe operational environments are areas least likely to have been fully tested. Operational evaluation is sometimes the first opportunity to subject the system to conditions closely resembling those that it will be designed to encounter. 3, interoperability, compatibility with external equipment subject to non-standard communication protocols and other data link characteristics make it essential to test the system when it is connected to the same or functionally identical external elements as it will be connected to in its operational condition. And 4, user interfaces, how well the system users and operators are able to control its operations. That is, effectiveness of the system human-machine interfaces must be determined. This includes assessing the amount and time of training that will be required, the adequacy of training aids, the clarity of displays, and the effectiveness of decision support aids. Well, let's consider an example of operating and operational evaluation of an airline. And so the function of a commercial airliner is to transport a number of passengers and their luggage from a given location to remote destinations rapidly, comfortably, and safely. Its operational configuration is illustrated by the so-called context diagram that we're showing here in the figure. The diagram lists the principal operators, the principal operational inputs and outputs, together with the ambient and such environments that contribute to and affect the operation of the system. The principal input besides passengers and luggage are fuel, flight crew, and navigation aids. Numerous secondary but important functions, such as those relate to the comfort of the passengers, that must also be considered, are omitted from the figure for the sake of clarity. The operational flight environment includes the flight medium with its variation in pressure, temperature, wind velocity, and weather extremes, which the system must be designed to withstand with minimum effects on the primary functions. So the figure, we have A and B. So what we were talking to is the one on top, and then on the bottom corresponds to is the corresponding diagram of the airline in an operational test mode. So a comparison with the portion on top shows that the test input duplicate the test inputs duplicate the operational inputs, except for most of the passengers and luggage are simulated. The measured outputs include data from the plane's instruments and special test sensors to enable evaluation of performance factors related to efficiency, passenger comfort, and safety, as well as to permit reconstruction of the causes of any in-flight abnormalities. The operational test environment duplicates the operational environment, except for conditions of adverse weather, such as wind shear. To compensate for the difficulty of reproducing adverse weather, an airline under test may be intentionally subjected to stresses beyond its normal operational conditions so as to ensure the sufficient safety margin has been built in to withstand severe environments. In addition, controllable severe flight conditions can be produced in wind tunnel test in specially designed hangars or in a system simulation. Okay, well, we gave an example. Now we'll give some more details, and I'll just give some highlights, and there'll be some more information from the textbook that you can refer to. So I'm showing a figure here for test realism versus cost, but let me continue to be talking about the main features of what we're trying to convey in this section, operational test and evaluation. So we need to be thinking about the test planning and preparation. And so the test plans and procedure, which are used to guide operational evaluation, not only must provide the necessary direction for conducting the operational test, but also should specify any follow-on actions that for various reasons could not be completed during previous tests or need to be repeated to achieve a higher level of confidence. Should also be noted that while there are general principles that apply to most system test configurations, each specific system is likely to have special test needs that must be accommodated in the test planning. the extensive scope of the test planning for the experimental evaluation of a major system is illustrated by the provisions of the TEM. It requires that the plans for operational test and planning should in part list critical operations, define technical parameters, define operational scenarios, define the operational environment, identify test articles necessary, state the test personnel training that is required. And for the test evaluation and scope, the evaluation planning must include definition of the appropriate scope of the effort, how realistic the test conditions must be, how many system characteristics must be tested, what parameters must be measured to evaluate the performance, and how accurately. So there's more details here. And so for this figure, we're giving an example of looking at the test realism versus cost. And so maybe we don't need to get to the flat part up here. And so we can be optimizing the cost somewhere in the middle. So there is a lot of information in this section. And so I'm not going to go through all of this, but continuing on, there is a section that talks about several other points here on test planning and preparation. And so things that need to be thought about are the test evaluation scope, setting up the test scenarios, then defining the test procedures, and then also having any analysis plans that you can't do everything if you're not in the relevant environment. Training needs to be taken care of, that people need to get to a point where they're sufficient and qualified to be able to operate the test, the operational test. We also need to be thinking about the test equipment and the facilities. The test equipment can be very complicated, and there needs to be enough rigor that it can effectively measure the equipment that we're trying to test. And then in terms of the test conduct, we have to be making sure there's adequate test support, making sure that it's clear how we're going to go about getting the data from the test article, so the acquiring of the data. We have to be mindful of the human-machine interfaces and having representatives of the user community there under certain circumstances, or at least the customer would be helpful. And of course, making sure that we're always holding to having a safe environment. We'll finish up with this last section, this last slide for this section, and thinking about the test analysis and evaluation and what we're actually going to be producing the reports. And so the objectives of operational evaluation have been seen to determine whether or not the system as developed meets the needs of the customer. That is, to validate the performance meets the operational requirements. The depth of evaluation data analysis varies from go, no-go conclusions to detailed analysis of the system and all major subsystems. Under some circumstances, an independent evaluation agency judge may step in and help to give insight in that a new system is deficient in meeting the user's operational goals to a degree not resolvable by minor system design or procedural change. And so there is going to be some mechanism that's going to be laid out for that. Well, let me just focus just briefly on here the kind of reports that are going to be produced. So in terms of test reports, because of the attention focused on the results of the operational evaluation test, it is essential to provide timely reports of significant events. It is customary to issue several different types of reports during the evaluation process. First, quick look reports. These provide preliminary test results immediately following a significant test event. An important purpose of such a report is to prevent misinterpretation of notable or unexpected test results by presenting all the pertinent facts and placing them in their proper perspective. There's status reports. These are periodic reports of specific significant test events. They are designed to keep the interested parties generally aware of the progress of the test program. There may be an interim report of the cumulative test findings at the conclusion of the test program, while the data analysis and final report are being completed. And the final thing is the final evaluation report. It contains the detailed test findings or evaluation relative to the system intended function and recommendations relative to its operational suitability. It may also include recommendations for changes to eliminate any deficiencies identified in the test program. So in terms of the human factors testing at the system testing level, the human machine interactions can include displays, controls, and wearable systems. These activities that represent requirements across the mission lifecycle can be assessed for workload, understandability, and tolerance to error. And tests can be evaluated different system configuration, workspace layout, or multi-user operation. So there's a lot more details in the textbook for this, but in terms of giving this yet one more perspective we need to be thinking about in system tests, I wanted to include that. Okay, well, in terms of test planning and preparation, integration and evaluation, quote, materializes the system as a whole and synthesizes a functioning total system from individual components. These activities solve any remaining interfaces, interaction problems. So we have this main document here, the TEMP, the Test and Evaluation Master Plan, that is developed at least for defense systems. It'd be something slightly different if you were doing something for NASA, or other agencies or other customers. System requirements should be reviewed prior to preparing the test plans to allow the customer requirements changing during system development. Late injection of technology advances always poses risk, and so that's something that you always want to try and to avoid and critically review as a systems engineer. Key issues during system integration evaluation includes intense management scrutiny during system testing, changes in test schedules and funding due to the development overruns, and readiness of test equipment and facilities. System test equipment designs must meet exacting standards and accurately must be more precise in the component tolerances. We've mentioned that a little bit already. And reliability must be high to avoid aborted test. And finally, design must accommodate multiple use and failure diagnosis.